and allowing us to start again with this series of seminars. And I'm really delighted that we start with Aleksandra Walczak. I've met Aleksandra when we had just moved to France at an ERC interview training session of the Ministère de l'Éducation. And at least in her case, this has been very successful because since then she's been awarded a starting ERC grant, a consolidator grant, and a proof of concept grant. So I suggest that you go to these interviews either to meet friends, as in our case, or to succeed. Aleksandra is a biophysicist with her main expertise being genes and the immune system. She received her PhD in physics at the University of California, San Diego. And after that, she was at the Princeton Center for Theoretical Physics as a fellow, before joining the CNRS at the École Normale Supérieure, where she's now Directrice de Recherche. She was awarded the Grand Prix Jacques Herbrun de l'Académie des Sciences in 2014, and the Bronze Medal of CNRS in 2016. And as I said, her main expertise is the immune system, but we heard that she works also on the dynamics of bird flocks. And so that's what we wanted to hear about. And so she will talk about learning interaction structure in bird flocks from data. Thank you, Aleksandra.
All right, so share screen. Here we go. You see my screen? No, you don't see it. Do you see my screen? I can't hear you.
Yes, sorry.
All right. All right, well, thank you very much for the invitation. Always happy to be a guinea pig. Not sure about that. I didn't know this is, I'm gonna really be the first. And thank you for coming to hear about something completely different, so birds. I guess the organizers chose birds because it's still staring at the sky, so it makes you happy, but here we go. So first of all, let me just start by acknowledging my collaborators, because this is, as always in this field, a highly collaborative effort that's been going on over quite a few years now, and these are my main theoretical collaborators listed here. With Irene Giardina and Andrea Cavagna playing double fiddle of theorists and well, observers in this case. Observation is rare in biophysics, and this is the group who take data. So let's start, but let's go on. Sorry. Something's wrong. I can't change screen. I can't change slide. My computer died. Oh no. Okay. This is great. Okay, now it's going. But am I still there? I'm still there. Okay.
Yeah, you're still there, but we see you, not your keynote.
Yeah, it seemed to have died, so now here we go again. Okay, now it works. So let's start with the movie. Everybody loves a movie, and this is what we'll be talking about. This is the natural phenomenon in question. These are starlings, so birds. They're ugly, not interesting. They typically eat your cherries. But here you see them moving very collectively, moving together in cohesion. What they're actually doing is they're going down to roost. This is taken at Rome's Termini station. They're going down at night from the mountains to roost, so to sleep in these trees. And you can see basically the idea is that there is this very, very collective motion of them forming domains and coming together. Yet, as I'll show you, there is no leader bird. So we can actually take, you can take data from three cameras at the same time, stereotypically, and then you can put this together and you can see, actually analyze the data. So this is what it looks like. This is these are velocity vectors, And so you see this very coordinated motion. And if you subtract away the center of mass, so the fact that they're all moving in this direction, and just look at the local fluctuations around that motion, you see these domains. So you see these, that it's not just the fact that they're moving in one direction, it's actually the fact that they're trying to align and do the same thing. So that's what we're saying. So you're saying some global order emerge, and the question is, where does it come from? So somebody said that, well, they're not self-organized. This is a self-organized system. There's no leader bird, but yet you do see this very strong polarization. So we can look at this again in more quantitative terms. Specifically, we can calculate the correlation function between the fluctuations in the direction with respect to the main direction of motion. So this is what this is. This is the correlation function in the fluctuations as a function of time. And you can see that your eyes don't fool you. There is an emergence of a non-zero correlation length, meaning there is a region which is marked by this distance psi, over which the birds do align and correlate and move in the same direction. And if we look at how this distance scales with the flock size, so of course different flocks have different sizes, you see that it actually scales, it scales with the flock size, meaning that there's no characteristic length. So there's no one fixed psi which sets the scale over which these birds will coordinate. And that's a signature of scale-free correlations. So this suggests that it's, well, that there's no characteristic scale to this problem. It suggests self-organization, and that there's no centralized command, and it also suggests that the correlations are long range. So we'd like to understand more where they come from, and we'd understand the equations of motions underlying this system. So unfortunately, we don't know much. Of course, you know, we know, I mean, we know Newton's laws basically, but this is sort of irrelevant if you want to understand where the collective behavior comes from, where the self-organization among many elements comes from. So we're sort of set back 200 or 300 years to a situation where we have data, we can collect data, but we lack the basic equation that we could check against data. So what we're going to try to do is, on one hand, do what we usually do in this field of, say, condensed matter physics, which is try and write down some sort of equation and predict observables. But on the other hand, what we try to do, and this is what I'll be trying to do, what I'll be talking about today, is actually learning from data. So taking data and then trying to see whether we can figure out what is the underlying equation of motion. So here you see Stefania actually taking data in Rome, and this is how it's done. And what we're going to try to do is do this part and then verify doing that. Okay, so what level of description are we at? We're basically at the level of description where we really don't care about those birds. We don't care about each particular bird, but we think about them just the same way we think about gas particles in a box. What we'd like to do is we'd like to figure out what's the distribution of velocities of the birds as an ensemble. So this is akin to figuring out finding out what's the Maxwell-Boltzmann distribution, where, as I said, we don't really care what each particle does, but we care about the overall distribution of the different gas velocities in a box. Only, you know, where do we start with? Here we start from energy considerations. Where do we start with? And I guess another important point to note at this point is that we really are, since we're looking at it as an ensemble, we're aiming for a statistical description of a stochastic system. And this will come back a bit later. Okay, so how can we learn this? We can learn this if we if we constrain something we know from the observations. And in this case, we will constrain the observations that I mentioned. We will constrain the correlation function between the orientations. So this is where we actually look at the velocities mapped onto the center of mass. So the fluctuations around the main direction, it doesn't matter, but we will basically try to constrain our probability distribution to include the observables that we have measured directly from data. So we will try and build a probability distribution that constrains the correlation functions. And this approach, there's an approach to doing this, which is called the maximum entropy approach. And I'll describe that in more detail now. So, okay, so what our basic observable is the direction of flight of each bird. And we want to learn, so this is just the rescaled velocity vector of each bird, and we want to learn the probability distribution of these directions. We're going to take a maximum entropy approach, which was where we're going to say we want to find the distribution that makes the smallest amount of that constrains the distribution in the as little as possible. So that means we're going to find a distribution that maximizes entropy. Entropy being a measure of diversity here. So we want to find a distribution that can be as diverse as possible, so that maximizes entropy in the physics sense of the entropy for this probability distribution. Yet at the same time, we want that distribution to capture correctly the observables that we measure in the data. So we want the correlation functions that we're going to calculate from this model distribution to match the correlation functions that we see in the data. And so how are we going to do that? Well, we're going to optimize functional, where our functional is going to maximize the entropy with the constraints of the observables, where here I will just constrain the second order moments, the correlations, and I'm going to assume that my probability distribution is the probability distribution so that it's normalized. And I'm going to impose these constraints using Lagrange multipliers, the lambdas, and Lagrange multipliers for each set of pairs of correlated birds, which I'm going to call JKL, and you'll see in a second why. But the basic idea is I want the least constrained model, the one that maximizes entropy. However, I still want to constrain the observables that I see. Okay, now I enforce them using Lagrange multipliers. And when I turn the crank on this, I can turn the crank. It's just an functional optimization. I find the form of the probability distribution that takes this form. And now, if you're a statistical physicist, you suddenly get a warm and fuzzy feeling, and you're at home because you see this Hamiltonian here, you see this energy in this exponential that you've seen in textbooks since you were of a certain age and people have worked heavily on. Okay, so this corresponds to a classical Heisenberg model in a lattice, or a three-dimensional generalization of an XY model. There's different cases. I suspect that some of you may be getting a warm and fuzzy feeling, but maybe not all of you. So if you're not, just let me tell you that there's people in the world that get very excited when they see something that looks like this. Okay. Now, the main difference between what we get here as a form of a distribution and what we actually get in textbooks is these JIJs, because in textbooks, we make a lot of assumptions about the form of JIJs, and then we can calculate scalings and find phase transitions and other interesting things. Here, these JIJs are constrained by data. This is where the data goes in, and we can this is basically where the properties of the system are hidden. maybe the details of the system. Of course, the general properties also are incorporated in the function. But that's what we get. So we're able to learn, in a way, the equivalent of the Maxwell-Boltzmann distribution for this system. We're able to learn the probability distribution that tells us the global behavior of the ensemble of the direction of flight of a flock of birds. Okay, so that's the recipe. Now we actually have to do it. So to do that, we're going to put in a parametrization, because as I suspect you also know, and you have this problem in your field, data is limited and we have many parameters. So here we're looking at all pairwise correlations. So we have a lot of parameters. So we're going to make a parametrization where each bird interacts with strength J with its nearest neighbors, but is with its NC nearest neighbors, and then it doesn't interact with any bird that is beyond NC. And this is, you can again turn the crank and show that this is equivalent to constraining a correlation function of this form, where the birds are only, you average over birds in a given vicinity. Okay, so first we're going to actually learn these J's from data. And for now, I'll just be using single snapshot data. I'm learning a static distribution, and we'll get to the movies later. So we can do it. I won't bore you with the details. Here you see in red the same distribution for the correlation function between pairs as a function of distance, the pairwise correlation function as a function of distance. In blue, you see our maximum entropy fit. So we fit these J's, we fit the NC, so the range of how far they interact with, and what's the strength of this interaction, and you see we're able to reproduce the data. And we can also reproduce higher order moments, such as the fourth order correlation function, which basically describes the interaction between pairs of birds at a given distance, and then different pair, and how these pairs interact with a different pair at the second distance. So this doesn't really matter. It's a high order correlation function. This is something that we put in when we learn. This is something that we don't put in, but we're still able to get out. So this proves we're not overfitting. Okay, so let's get back to the question of can you get global order? So the answer is yes, you can get global order. Can you get global order from local communication? Yes, you can get global order from local communication, because what our form of our Hamiltonian tells us is that you only have pairwise interactions with the birds within a given range. So of course, to answer this fully, we need to say something now about what is this range, because if this range is everybody in the flock, then that's not really local anymore. So let's take a plunge into that question, and specifically let's take a slightly different twist on it, of asking what kind of interactions there are between these birds, whether they're metric and or topological. So what do I mean by that? A metric interaction is that if I'm this bird, I will interact with all the birds that are within a fixed radius of me in terms of meters. So shall I interact with anybody who's within 10 meters of me. So then if I increase that radius to say 20 meters, well, naturally I'll increase the number of birds I interact with. A topological interaction means that I interact with a fixed number of birds. I'll always interact with 6 birds. So if I increase or decrease, if the density of the flock gets larger, then I'll still interact with 6 birds. They'll just be closer to me in physical distance. So if I now look at the scaling of the number of interacting birds with the density of the flock, in the metric case, I expect a linear scaling, whereas in the topological case, I expect that the number of interacting birds doesn't change with density, which is basically shown on these cartoons. So what's the answer? The answer is that the number of birds you interact with absolutely does not change with density. It's completely constant. There seems to be a magic number. And so that shows that the interaction between birds is topological. So people have said weird things about this, like when this means birds can count or whatever. I'm not interested in getting into bird psychology here. Okay, it's just the fact that they do correct for changes in density, and they sort of that they make the decision based on a fixed number of birds. The other thing to see here is if we sort of remind ourselves about this question that we saw scale-free interactions, so we can ask how is the interaction range constant with also flock size? And it is constant with flock size. So the interaction range, meaning the number of birds I interact with, is always the same, and it doesn't matter if I'm in a big flock or I'm in a large flock. However, the correlation range scales with the flock size. So this really points to the fact that I'm having local interactions on a small scale that then translate into a huge correlation length, right? This is the difference between interactions, which are JIJs, and correlations, which is the observable effect that I'm seeing. So I'm really getting global order from local interactions. I have a finite interaction range, but I'm seeing within, within the box size, if you will, an infinite interaction range. Okay. So here you see roughly on the scale, this is the correlation range, this is the interaction range. So it is much smaller. And you can say, well, why should I be surprised? And in fact, I shouldn't be surprised, because we're in a limit of having Goldstone's theorem, which means that basically I have a zero mode in the system. So what we're looking here, I'll remind you, is that we're looking at the orientation of flight of these birds. And basically there's global orientational symmetry, meaning that if I fly this way or I fly that way, there's no law of nature.
Sorry, Aleksandra.
Yeah.
I interrupt you because there's a question in the chat by Simon Prunet. Maybe we'll ask it. Okay, fine. I'm unmuting you, Simon. So please ask.
Okay. Now, it's just a question when how do you estimate the number of the NC from data itself? So I see for the correlation function, but how do you?
It's the same. So it was here when I made this assumption. So thanks for the question, by the way. So okay, it's what we do in practice is we do a likelihood estimation, and once we've made this assumption, we do it step by step. But basically, it's two parameters in the problem. Now we have J is kept fixed, so then we just have to see what is the NC that maximizes the likelihood of the data given this model, and we find the diff for this given NC. Does this answer your question? Or?
Yeah, absolutely.
Okay, and it's fixed, right? We don't pick different NCs in different parts of the flock. Okay, thanks. If you have any other questions, because, you know, I as I said, we, you know, it's helpful for me if you ask questions. All right. Anyway, so there's no preferred direction of flight, right? There's no, I mean, we're not talking about the you know, we're not taking into account gravity, because I'm not asking whether birds prefer to fly up or down, but in a given plane, whether they fly this way or that way, it really doesn't matter. So basically we have no, we have a global orientational symmetry, so we have a zero mode, so we shouldn't be surprised we get scale-free fluctuations. Okay, but nevertheless, it wasn't obvious that we're in this limit at all, because it wasn't obvious that there's a small interaction range. However, we talked about orientation, so we talked about the direction they'll be flying in and fluctuations in this direction, but now we can look at the fluctuations of the modulus of the speed, right? Birds also can go faster or they can go slower. Just like certain people I just found out really like motorcycles in this audience. So, okay, so we can look at this correlation functions of the speed as a function of flock size. And again, we see the same scale-free behavior. And now this is more surprising, okay? Because as we say, orientation is arbitrary, there's no preferred direction of flight, but velocity has physical bounds, meaning that if you're a bird, you can't fly faster than a plane, at least in normal circumstances, because I guess these days, if you go to Roissy, any bird flies faster than a plane that's not moving at all. But you understand what I'm trying to say. Basically, here we have physical bounds. We have something that limits the behavior. So we should be surprised we're getting scale fluctuations, because we would expect speed, so the modulus of velocity, to be a stiff mode and not a soft mode, not a zero mode. Okay, so, but we're gonna play the same game. I'm not gonna bore you with the details, but we're going to now try and learn the probability distribution of the velocity of different birds, and we're going to do it in the same way. We're going to do a maximum entropy approach. So again, the most general, most diverse distribution, but constrain the two first moments of the speed, so the mean and, well, effectively the variance. And we're also going to constrain the global alignment index, because the birds are still aligned. We're still interested in this property of coordination. So again, if we turn the crank, we get this form for the probability distribution, where we now have two terms. We have a similar term to what we had before, which is the coordination of the velocity with the neighbors. So birds are basically looking out and seeing how fast the neighbors are going. But we also have a term which corresponds to individual speed control. So this comes from here. And this individual speed control is basically, it's like your internal odometer. I was told not to say odometer, but you know, basically an odometer is the thing in your car which tells you how fast you're going, right? So each bird has some internal sense of how fast they can go, but it's also looking around, so that's the red term, but it's also looking around to see how it should align and interact with its neighbors. So that's the blue term. All right, again, we can fit the data. Again, we parametrize it with a J and then C to not bother about overfitting. So we can fit both the orientation correlation function and the speed. And then we can ask the question, what are birds doing? Are they listening more to their neighbors, or are they listening more to themselves? And it turns out that the ratio of how much birds listen to themselves to how much they listen to their neighbors, which is this, is small. So that means that birds listen more to the neighbors than they listen to themselves. And we're actually in a limit of this being so small. So this quantity can also be related, again, through a crank that I won't be showing you, to the correlation length. And so if this is very small, then the correlation length is very large. So as how much they listen to themselves decreases, the correlation length increases, and we're in this limit of, that's where the data is. We're in this limit where we have a very large correlation length. So the birds are really not listening much more to the neighbors than the listening to themselves. And in that sense—
Okay, Aleksandra, I just interrupt you again because I have two questions in the chat. So there's one from Christophe. So Christophe, I unmute you. Sorry, please go ahead. Demandez à doesn't work for some reason.
Yeah, I can hear you, I think.
Okay. Christophe?
Je suis devant l'école. Pose la question à ma place, s'il te plaît.
So Christophe was asking whether the velocity you are talking about is the absolute velocity or the relative velocity.
It's the relative velocity. We integrate out the center of mass motion.
Okay, and Raphael had a question too. So Raphael.
Hello?
Yeah.
Ouais.
Yeah, no, I wanted to ask whether gravity doesn't play any role. You said that
Yeah, but once we integrate out the center of mass motion, it doesn't. We're really looking at fluctuations. Okay, so let me take a step back. So what we're really interested in is the coordination aspect. This is a very good question. You could ask a different question. You could also ask, why the hell do the birds do this, right? And this is a valid question. And if you look why they do it, as I said, they're going up from mountains that are that cool off at night, and they go down to sleep in warm trees. And the motion, the sort of the center of mass motion looks roughly from a large scale like this. And there's a lot of interesting effects that due to thermal, convection, well, gravity, and you know, but it's more then you have more of a problem of sort of putting a feather in a hot pipe and having it go down only in an active system. So there is an interest in that, but that's not the question we're asking here. Does that answer your question?
Okay, yeah, thanks.
All right. Anyway, so these birds are critical, basically because of this very small parameter and generating this very long range correlation function, which is sort of, you know, it's like an opalescent phenomenon, but that's critical in that sense, not necessarily of water and ice. All right. So, and what, as in the sense of questions of who cares and what does it mean for birds? Well, they're really in a limit where they're listening more to themselves than so they have little self-control. The complete pushovers, they'll do what they're told, yet they come out to be completely ordered. So that means that in terms of the physical word susceptibility, which means the response to a perturbation, the system is very susceptible because it has a long range correlation function, so it can transmit information very, very quickly across the flock. So it can have a response, say, to a predator that's very fast, and that's thanks to the long correlation function to the basically critical point that it's finding itself. However, all of this comes from complete self-organization and strong interactions between themselves, not from some external field. All right, I thought I guess I have about 5 minutes left. So as I promised movies, so let's get to movies. And just to give you some context, birds are a prototype of what's called active matter, of a system where we say out of equilibrium dynamics are important. It's clear it's out of equilibrium, they're living, they consume energy, they move around also, but the main part of the activity comes from the fact that the network rearranges. So we've been looking at this static picture, but that's of course incorrect because birds do move around with respect to each other, and there's a rearrangement of the network. And that's the main source of the activity. And why is a source of an activity? Activity means being out of equilibrium, basically, I wanted to say something specific about this, but I forgot. But basically, okay, the idea is it's not an equilibrium system, right? There's no equilibrium distribution, and in fact, we've been making a sort of proxy of assuming a quasi-equilibrium distribution. So now let's go in and check this. Again, what we're going to do is now build a maximum entropy over trajectories. I won't go into the details. This is a novel technique we developed. It's harder. What it corresponds to at the end of the day is a sort of collective random walk where the position again, we're back to the orientation description just for simplicity. The orientation of a given bird depends on its alignment with the other birds, but it's a random system. So we have now introduced temperature in the problem because we have dynamics. So at the Langevin description of the system, this is actually what comes out from, again, turning the crank at the level of the probability distribution and the maximum entropy approach. And in the limit of in the equilibrium limit, so when the network does not rearrange, we recover the equilibrium distribution we had before, but now with J over T instead of JT, right? So the main thing here is now we introduce a new parameter, temperature, which describes dynamics. Okay, so we then can do a fit. We can do the dynamical fit with the Langevin equation, and we can do the equilibrium fit. And this is fitting, again, the NC and J over T, since that's the only parameter that can be compared. But here we can actually fit J and T separately. And we do the two fits, and we see that the dynamical inference and the equilibrium inference gives us exactly the same thing. So what's up with active matter, right? As I said, this is a prototype system of an out of equilibrium system. Everybody gets excited about it. Everybody will show you these birds when they're trying to motivate their work out of equilibrium. What's going on? Well, what's going on is the following. There are two timescales in this problem. The first is the relaxation timescale of how fast birds align in the local neighborhood. So basically that was it. Let's do it again. The bird aligns with everybody around them. Well, with the NC nearest neighbors. The other timescale is the network rearrangement timescale. So how fast does the network change? So that's the change of the network where, you know, you change who your neighbors are. The sort of this timescale, we can figure out the scaling of it. It scales as the interaction strength and NC, how fast they relax, right? That's the strength of the interaction. And how fast the network rearranges. Well, we can calculate this from the correlation function of how fast the network changes. So we can get these two timescales. And if we do that, and we do that for these flocks, we find out there's a separation of timescales. So basically, birds relax locally, so they align with the neighbors much more quickly than the network changes. So that means we're in an adiabatic regime. We have a strong separation of timescales. The relaxation timescale is much slower than the network timescale. At a given time, the birds essentially see a quasi-fixed network. They equilibrate in it. Then the network slowly changes. They equilibrate again. So we're in a quasi-equilibrium regime, and that's why this static inference works equally well. Of course, in simulations, we can go out of it. We can go into a regime where the two timescales are different, and then we can show that the dynamical inference actually, which is then correct for what we put in, is very different from the equilibrium one. So that's to sort of, I mean, that's in a way the punchline, that at least for the straight motion, birds, although they are an out of equilibrium system, behave very close to equilibrium. And we have been able to show that directly from data, and in a way that was a sort of a big negative surprise. However, birds do other things. So what I told you about here is the simple motion of just, in a way, flying straight, but they also turn. So when they turn, well, they turn, and if you look at how information propagates in the flock, so you can either look at how far is the bird, well, a bird X meters away, what time will it turn after a given bird has turned? That's what's shown here. And you see that the information transmit scales with T. You can also look at the dispersion relation and you reach the same conclusion. But you see this ballistic transmission of information, okay? Whereas in a diffusive system, which is what this is, right? This equation predicts diffusive behavior in time, should be square root of T. So we have a much faster transmission of information than we expect from this equation, okay? Which is sort of exemplified here. If this is the start of the turn, the bird turns here. When will the bird here turn? So in this model, we have a slow transmission of information, which will look like this. So you'll see some birds that have turned and some that haven't. Whereas in a real flock, it's actually fast, and we see this very rapid, coordinated motion. And so that implies it's an inertial system. If we want to get this ballistic behavior, we need to add inertia, so a mass, on top of to our damping. Okay, and that's what we'd like to do now. We'd like to infer these parameters. But it turns out that inferring inertial stochastic dynamics is way harder than everybody thought. Why is that? Okay, so this is our basic idea. We now have mass, we now have damping, we have interactions we had before, and of course we had noise because it's a stochastic system. And the problem is, if we look at data, what do we have as data? We have discrete, in a way, positions. We have the S variable, so we have the orientation. We don't have S dot. We don't have the equivalent of velocity. We don't have the, we can only calculate S dot as the difference of S's. We have a discrete time series. And it turns out that often, we have this sort of physics picture, but we have this wave equation, but when we're trying to connect it to real data poses problems, okay? And so you can say, okay, big deal, approximate your S dot as a difference of S's, so, approximate your velocity as a difference in positions, and you can do simple discretization, basically say that V is delta X to second order, and it turns out that you will fail miserably in this setting. So if you compare the simulated to the predicted in this case, you get, in this case of a simple discretization, you're off by a factor of exactly 2/3. Again, you can show analytically why it is. You need to go to higher order to get the correct agreement, to get a slope 1 between what you put in and what you get out. And why is that physically? Because you get a coupling between inertia and noise propagations. And this is a coupling you don't get if you don't have inertia, because it's not a coupling between damping, but the inertial term and this term and noise propagation. So again, if you don't have a stochastic system, you don't have this problem and you can do this discretization without any problems. But it turns out that there's a strong coupling between these two terms that actually matters when you're trying to fit discretized models. And this is nothing to do with birds. It's a very general phenomenon. It's also there for the stochastic harmonic oscillator. You get the same factor of 2/3. So that's where we are. We're trying now to put this correct inference into data and actually learn whether the inertial terms for birds matters more than the interaction term, and more than the damping term. So whether they're really, which damping regime are they in, and what kind of behavior depends. All right, so I'm done. I basically tried to show you that you can take data seriously, but it's requires some work, and you can develop methods, but data can still guide you to try and figure out what are the right equations of motions for system for which we don't have first principles equation of motions, and maybe we're not so interested in deriving them from the bottom up, but we want to get an effective idea of a collective phenomenon. So that's it. Our interest now is to go into long timescales and figuring out where the active parts or the non-equilibrium dynamics really matters for the behavior of this system. Thank you.
Thank you very much, Aleksandra. This was really awesome. I think it was the perfect level for us, or at least me. So now, people in the audience, if you want to ask a question, so you can either write it in the chat and I will see it, just write it to everyone, or raise your hand in the participant window. And we start with Jean-Baptiste.
Is it working?
Yes.
Okay, perfect. Okay, so thank you very much for this presentation. So the first thing I wanted to say is I should reassure you, you were not that far away from astrophysics, because it's a kind of a funny thing. The model of classical Heisenberg spin you mentioned is formally exactly the same model one needs to use to describe how stars are changing of orientations in galactic nuclei, so around the supermassive black hole. So birds around themselves and stars around galactic nuclei, exact same fight. So the question I had had two parts to it. The first one is in order to infer your equilibrium, you started by maximizing Boltzmann entropy, which is a fairly usual approach. But my question was, why did you pick this one particular entropy? Because in particular, your birds have additional constraints they need to satisfy. They cannot overlap. So there is some pressure from it. You cannot pack them as much as you would want. And so it's not so obvious that this functional should be the one you want to maximize. And the second part to this question is, you mentioned at some point that you were modeling the interaction between your different birds as let's say, a neighboring interaction. And I was wondering whether or not we should describe this interaction potential, not only with the respective position, but should not we also account for the respective velocities? So should the interaction potential not only depend on position, but also on velocities?
Okay, so let me start from the first. I mean, these are excellent questions. So ultimately, you're right for the first one. What we did is we kind of cheated. So, this is the cheat occurs here moment. What we did, so, you're suggesting to basically optimize, put in a PV term, like a pressure volume constraint, right, to go to a different free energy functional. And so since we cannot measure pressure easily, what we do instead is we fix the boundary birds, which accounts for that. So it's sort of, let's say, it results in the same, but it's a dirty way of doing it. I think it's a very good suggestion to try and think about minimizing other free energies. And in fact, so what we've been trying to do now is to understand the constraints coming, we think about this in terms of surface tension, well, which is essentially the same thing as pressure, but in 2 dimensions. And so we've been trying to do that and we've done it in a continuous version of this theory. So theoretically, there's a limit of this, which is the hydrodynamic limit. And we've also shown that birds are actually not in the hydrodynamic limit, but since we can turn the crank more easily there, that allows us to get intuition. And there's a question also, how do you relate that effective surface tension term to actual motion of birds? So birds don't like to be on the boundary, which you understand because they're gonna get eaten more quickly. And one of the things we're trying to do is see how we can translate those rules, those dynamic rules for bird motion into surface tension. So as I said, short answer is you're right. Then we cheated and then we're trying to fix it now. Your second question was, I forgot already, sorry. Remind me.
I think that you're still unmuted, Jean-Baptiste, I hope.
Okay, yes. So yeah, okay, it's working back. Let me just turn on the camera so you know I'm a physical person. So the second question was, should one also account for velocities in constraining the interaction potential? Because you're only discussing about neighbors to neighbors as a function of respective distance, but you could generically have an interaction potential that also accounts for velocity.
Yeah, I mean, in the second term, we constrained the velocities. Right, we said that they are trying to align the velocities. So, but we don't have, we don't have an interaction term. I mean, effectively we do. So let me show you what we're doing. Here, right? I don't know what this is. Here we're effectively doing that. In the when we actually start worrying about speeds. But I agree, you could put it in as you could break this up into alignment and velocity. And I think we have tried to do something along those lines. We just run into data overfitting problems, but I don't remember exactly. But I know we did think about that. We had maybe even in the paper we do something about that. It was just a while back.
Okay.
So.
Okay. Perfect. So if I can ask one last question. So A while ago, I had heard a presentation from Clément Cyr in Toulouse, who had presented similar things about.
So sorry. So they're the ones. They have a model for this pressure thing that I talked about. Okay, so this adhesion thing. So what they worried about is why it stays together, and that's what we've been cheating on so far. And now we'd like to put it together.
I see. And so the last question I wanted to ask was, okay, so it works for birds, it works for fishes. So does it also apply to humans in some regimes?
People do this, like, you know, people like Renault do this to make sure that the self-driving cars don't drive into us. I mean, I think you know the answer yourself, how well that works out. And for now, you know, but yeah, another thing is crowd control, behavior during demonstrations, concerts. So, you know, the police uses these kinds of algorithms too. So people do use it now, you know, the limitation of how well this works. Humans are always complicated because, as I said, I don't care about bird psychology. It's a bit harder not to care about human psychology. But there are definitely limits where human crowds depend in predictable ways like this. So yes.
Okay, thank you very much. Thank you.
Okay, so now Jean-Pierre.
Yes, hello Aleksandra, it was really a great talk. It was really fun to listen to that. I have a question about the description of some of the motions. Don't you think it's wave propagation could be considered in some cases, especially, for example, response to perturbation, or it makes no sense at all?
No, this is exactly what this is. This is what this is. This is a wave equation. I can show you the slide. I can show you a different version of this slide where it may become even more obvious. No, actually, I can't because I deleted it. But you can write this really in a way that you see purely the wave equation elements here and propagation. So yeah, that's part of that, you know, that's why we're talking about dispersion relations. That what we can do is we can calculate omega versus k and see how information is propagated. So the first part, you know, was a bit more simplified than that, but that's where it's going. And the question here is precisely how does information propagate in collective media?
And now Patrick.
Yeah. Okay. Hi, Aleksandra. Nice talk indeed. I had a very silly question. Since going back to your analogy, to your gallstone analogy, you're essentially breaking a symmetry. You're saying you're breaking some sort of a symmetry. And okay, I didn't have time to think about it a little more, but I was wondering, do you also form defects in the evolution of the flock?
Yeah, so actually in the flock, not so much. This is a great question. And you may hear about it sooner than you think, because this is a very big deal. In bacterial populations, people see topological defects and they see positive and negative poles, and then they see the defects annihilate, and you get everything you ever dreamed of in all these topological phases. So exactly spot on, and people see this in experiments, and it's super cool.
Great, thanks.
Okay, I would like to ask a question before there are more raised hand. So have you conducted experiment only on one type of birds, or this is general for all types of birds?
So I think Jean-Baptiste, so, you know, it's not true for geese, right? I mean, the key flying to the south business, you know, not all birds flock. But I mean, okay, after this talk, you may have seen these pictures on YouTube, but I guarantee you after this talk, you may actually find yourself looking at birds in the sky, and you do see this. You even see this in Paris. You don't have to go anywhere exciting. They do this. Okay, now you're really like, as I said, I don't care. I'm not an ornithologist. I actually don't care about birds. So don't ask me what species does it and what species doesn't do it. Starlings do it, but then also fish do it, as Jean-Baptiste mentioned, this fish schooling. And if you ever find yourself snorkeling in the south of France, it's amazing. You can swim and you can be the predator. You can break up a school of fish. It's a bit, in the Mediterranean, it's actually very much equivalent, although there's still a more a 2D system. This is really a 3D system, which is also exciting from the statistical physics point of view. But yeah, other birds do it too. This was really, they started doing it. The people who did it, Elena and Andrea, the bona fide statistical physicists. These were people that were calculating scaling exponents. And then one day they just decided to take these movies. That was some 15 years ago. It's a lot of work, but they were going to work and they were seeing it. So, but don't ask me what other species of bird does it. And I mean, in fact, if you see this, I can't tell you if it's a starling or not.
Okay, sounds good. Thank you. Now, one question from Huri Zepur. Okay.
Hello, do you hear me?
Yes.
As you mentioned, their flocking is very dynamical, and there is a sort of defects and so on. But I wanted to know, for instance, they very quickly separate from each other. Can this be, or I don't know, have you tried to model it by some sort of phase transition or something like that? Huh?
Yeah, no, so clearly this is a system that exhibits a phase transition, and here we're in the ordered phase. And actually one of the things, so, I said the system is critical. So it's critical between being ordered and actually falling apart, right? If you were on the other side, that it wouldn't be ordered. It wouldn't stay together. I think what you're really getting to is this question of timescales. As I said, we've managed to describe this so far on relatively short timescales, and that's part of the reason I personally believe we're in this quasi-equilibrium regime. To look at these kinds of phenomena, we need to look at longer timescales. But if you look at longer timescales, they start turning, they start doing things we haven't yet managed to correctly fully describe. So I think this is all for the future, and and these density fluctuations that sort of look like the flock is falling apart. The flock does separate sometimes. So I mean, I would say this is more like a separation into domains than actually a phase separation between order and disorder. But we don't really see disordered flocks. But we do see domain formation and then separate behavior. So this is all in the future at the level of connecting to data. On the purely theoretical side of studying these models to death, people have looked at that, and you can get that in certain regimes.
Okay, do we have any other lingering question? Okay, if not, we're already 5 minutes after the hour, so I would like to thank Aleksandra again for a very exciting talk. And I think that the next seminar will be next Friday. And I think Johan and Sandrine can correct me.
I'm not sure. There was a hole at some point in the agenda.
It's in 2 weeks from now, actually.
It's in 2 weeks. Yeah.
Anyway, thanks again to Aleksandra and to everyone who joined to be with us today.
Thank you very much. Bye-bye.